Collision theory is essentially a theory that is used to predict the rates of chemical reactions, usually gases, based on the assumption that to occur it is necessary for the reaction species to collide with one another. It was proposed by Max Trotz in 1916. In this experiment, collision theory allows us to determine the rate of our reaction, basically how collisions affect the speed of the reaction. From this lab, we know that increasing the concentration of reactant molecules leads to a higher number of successful collisions. When we increased the amount of KiO3 in the reaction, there were more collisions and the color change proceeded faster. When the solution of KiO3 was diluted with water, there were less collisions because the concentration was lower and the reaction proceeded much slower.
For part A of this lab, we took 0.05 molar of sodium metabisulfate and added 10 mils of a starch solution. In a separate beaker, we poured 18 milliliters of 0.05 molar of potassium iodate. We then took 6 small beakers, each filled with separate amounts of water and potassium iodate. In the first beaker, we had 5 milliliters of the potassium iodate and no water. In the second beaker, we had 4 mils of the potassium iodate and 1 mil of water. In the third beaker, we had 3 mils of potassium iodate and 2 mils of water. In the fourth beaker, we had 2 mils of potassium iodate, 3 mils of water. And in the fifth well, we had 1 mil of the potassium iodate and 4 mils of water. And in the sixth plate, we just had water. Once each beaker was filled with the correct ratio of potassium iodate and water, we then took 2 mils of the sodium metabisulfate starch solution and added it to each individual beaker, and then timed the reaction that it took for it to change color. Each reaction should be done separately and timed separately in order to have a correct measurement of how long it took, and the timing should be stopped when a bluish color would appear.
For many reactions involving liquids or gases, increasing the concentration of the reactants increases the rate of the reaction. For these reactions to happen, the particles must collide first, which is explained through the collision theory. The collision theory states that chemical reactions occur when molecules collide with enough kinetic energy to successfully complete the reaction. The higher the concentration, the more likely the particles are to collide into one another. This is seen when we chose different amounts of KLO3 and water to mix with one another. The higher the concentration, the faster the reaction occurred. The color change in this lab indicates a successful reaction.
In this diagram, it shows 4 different kinds of collisions that could happen. And the only one that would work is the first one, and that's because the hydrogen atom would have to be the one that broke the double bond. That's highly negative because of all the electrons. All the other ones would just cause the atoms to just bounce off of the molecules and no reaction would occur, but in the first collision, that would cause the double bond to break and cause a reaction to occur. And as you can see, like, there's more than one type of collision, so the more collisions occurring at once would be more likely for the first collision to occur and actually have a reaction. So this is why the higher concentration of having more of those molecules together would be more likely of having this first collision type occur and causing a reaction to happen. This is an energy profile diagram, and in this one, it's particularly an endothermic reaction. We know this because the energy level of the products is higher on the energy scale than the energy level of the reactants. Another key point on this graph is the activation energy, also known as the critical energy, and this relates to the collision theory because the amount of collisions that occur need to exceed this critical energy in order for products to be formed. So the critical energy and the activation energy are the same thing, and that's represented by that hump in the middle. In this last diagram, it shows 2 different concentrations of molecules in the same size container, and the one on the left has a low concentration, so it has less molecules and they're hitting less, which makes sense. And on the right, the high concentration have more collisions, which also makes sense. So you can relate this to like a party situation. If you're in a room and there's 10 people, it's less likely that all those people are going to interact than if there's same size room of 100 people. They don't really have a choice. They'll be stuck together and they'll be more likely to hit. So that's why higher concentrations have more collisions, and that's how they relate.